All right, let's illustrate the Gram-Schmidt process by doing 6.2.9, where the instructions are transform the basis, so they give us three vectors, basis for R3, into an orthonormal basis using the Gram-Schmidt process. Okay, so we trust them that they've actually given us a basis, a linearly independent spanning set for R3. Gram-Schmidt process says, we'll denote those vectors as A1, A2, A3. All right, so following the notation we set up in terms of the section, we always started out by creating an orthogonal basis by letting the first vector, v sub 1, this will be the first vector in the orthogonal basis. We'll take care of the normality part here at the end. First vector is 1, 0, 1. All right. Now we had a process, an iterative process, where we choose the second vector, v sub 2, in the orthogonal basis to be the second given vector, a sub 2, minus the projection onto the first vector, v sub 1, of this second vector. And we could also express that as a projection onto a subspace. So what we're doing is finding the components of a sub 2 in, if you like, a subspace W1 and a subspace W1 perp. So we're breaking away the piece of a sub 2 that lies in the direction v sub 1, more generally in the subspace w sub 1. It could be more than one direction. There will be once we find w sub 3 in terms of treating these as projections onto subspaces. First one's just a projection onto a vector. Easy enough. Let's see, that would be a sub 2 minus, to project onto a vector, we'll take a sub 2 dot v sub 1 divided by v1 dot v1 times vector v1. Okay, to emphasize, we get this scalar coefficient of v sub 1. Okay, so we'll calculate the dot products. You need to know this formula in terms of projections. Projections, when we had orthogonal bases, were easy, and we're creating an orthogonal basis. Okay, with the numbers we have here, let's see, a sub 2 is this vector, 0, 1, 2. All right, from that we'll subtract this dot product stuff, 0, 1, 2, dotted with vector v sub 1. V sub 1, here it is 1, 0, 1. Make sure you look in the right place. We're doing the computations largely with the v vectors that we've found, only minimally with the a vectors that we were given, with one possible exception that, oh yeah, well, the way we set it up, v1 and a1 are the same. Okay, so we just need to do the arithmetic on this. That is, we need to take those dot products. Dot products are easy. We'll get, let's see, minus 0 plus 0 plus 2. 1 plus 0 plus 1. Oh, nice. So we get 2 over 2, 1, 0, 1. If we'll do that arithmetic and subtract, so we're really just taking the difference of two vectors here, we'll have 0 minus this vector, so that'll give us a negative 1. 1 minus 0, and a 1. 2 minus 1, and a 1. So that'll give us the vector v sub 2. Okay, so now the pattern gets a little more involved, starting with v sub 3. Of course, we only have to find a v sub 3 because we're only given 3 vectors. So next, v sub 3. Okay, v sub 3 is a sub 3 minus the projection onto what we would call maybe w sub 2. And some of the notation we had when we went through the proof of the Gram-Schmidt process. What it is the span of the previous two vectors, v1 and v2. So this better illustrates the pattern of how we deal with finding a general v sub I. You take a sub I and you subtract the projection of a sub I onto the span of all of the v vectors you've already found. Projecting onto spaces is not so easy unless you have an orthogonal basis for those spaces. Well, I guarantee you v1 and v2 are orthogonal because we got them out of the Gram-Schmidt process. Don't believe me? Here's v1, here's v2. If we took a dot product, we get -1 plus 0 plus 1. Yeah, it's 0. So they actually are orthogonal. So we're on our way to an orthogonal basis. So since v1 and v2 form an orthogonal basis for their span, then here we'll get a3 minus, we can calculate those projections using dot products. We'll project a3 onto v sub 1. That's a3 dot v1 divided by v1 dot v1 times v1. It's a projection of a sub 3 onto v1. It's the same way we projected a sub 2 onto v1. Minus, if I distribute that negative sign there, also minus a sub 3 projected onto vector v sub 2. Okay, we'll compute that in terms of dot products as well. And there's the formula for for v sub 3 in terms of a sub 3 and the earlier v values. You want v sub 4, if we had to do that, sure. A sub 4 minus a dot product involving a sub 4 and v sub 1, minus a dot product involving a sub 4 and v sub 2, minus a dot product involving a sub 4 and v sub 3. So that's why it's iterative. Okay, so let's compute exactly what we get out of all those dot products there. A sub 3 is the third given vector, so that's 2, 1, 0. Minus, we'll do the dot product. 2, 1, 0 dotted with v sub 1, here it is, 1, 0, 1, divided by v1, 1, 0, 1, dotted with itself, 1, 0, 1, times the vector v1, 1, 0, 1, minus, let's see if I can squeeze it in on my little board here, a sub 3, 2, 1, 0, dotted with v sub 2, v sub 2, this is v sub 2, right? V sub 2 equals this, right? -1, I can't squeeze it in. Okay, so 2, 1, 0, dotted with -1, 1, 1, over the dot product of v sub 2 with itself, -1, 1, dotted with itself. Of course, we're just getting magnitude squared when we do that. There's some kind of normalization going on there, it seems. Okay, so we'll substitute in and get something exactly of that form. Let me take a look at it. We got a sub 3's in the right place. Should have an a sub 3 here, here, and here. Should have 4 v sub 1's here, right? Should have 4 v sub 2's there, v sub 2, right. So wish me luck on the arithmetic. So now we get 2, 1, 0 minus dot products. Let's see, 2 plus 0 plus 0. So we get 2, 1 plus 0 plus 1, 2 again. 1, 0, 1, minus a dot product, -2 plus 1 plus 0, -2 plus 1 is -1. In the denominator, we get -1 squared, as it's 1 plus 1 plus 1. We get a 3 there. -1, 1, 1 is the vector quantity. And so we get, let's see here, let's write it out in terms of components, and then I'll do the arithmetic. So we get 2 minus 1 minus a -1. So we get 3 negatives. We'll ultimately end up with a negative, it's a -1/3. So we get some fractions in it. And let's see, second components, we've got a 1 minus 0 plus 1/3. Third component, we've got a 0 minus 1 plus 1/3 again. All right, let's see, that's what? 1 minus 1/3, that's 2/3. 1 plus 1/3, that's 4/3. -1 plus 1/3 is -2/3. I've been through worse arithmetic problems. Let's bring that 1/3 out front and isolate the fraction stuff, as we often did. All right, so we get 1/3 times 2, 4, -2. Let me check my script, and that is correct so far. All right, equal signs starts over here. V sub 3 equals that thing over there. See, I'll have to erase part of this, so let me write out where we are at this stage. So V1, V2, V3, given as follows. See, V1 was right here, 1, 0, 1. V2 was given over here, -1, 1, 1. And V3 we just found 1/3, 2, 4, -2 is an orthogonal basis for the space we started with, and we started with the space R3. But that's not the entirety of the Gram-Schmidt process. We've created an orthogonal basis. We wanted an orthonormal basis. Okay, all we got to do is normalize those vectors. All right, now we might be fortunate enough to avoid fractions in the creating of an orthogonal basis, but when it comes time to normalize, the numbers are probably going to get a little uglier. Likely we'll be dealing then with some irrational numbers. Okay, so I got V1, V2, and V3 right in front of us there. Let's find their magnitudes. So we're going to need to normalize the magnitude of V1. Here's V1 would be 1 squared plus 1 squared, square root of, so that would be the square root of 2. The magnitude of, well, you know what, let me write it out. That's 1 squared plus 0 squared plus 1 squared square root of is the square root of 2. Norm of V sub 2, so it has components -1, 1, and 1, so we'll square each of those and then take the square root. Gives us a square root of 3. And the norm of V sub 3, let's see, we've got, you know, we could bring that 1/3 out front. A property of norms. If we multiply a vector by r and then take the norm, you can bring the absolute value of that r, that scalar, out front. So let's bring the 1/3 out front. We keep it isolated. Some other weird stuff's going to happen because now we've got to deal with squaring. So we get 2 squared plus 4 squared plus -2 squared, square root of, giving us 1/3, 4 plus 16 plus another 4. That was 4 plus 16 is square root of 24. Let's see, let's simplify that if we can. This is what? 6 times 4. So that's 1/3. Let's do this slow. My observations are students tend to struggle a bit with this. That's right, 24 is 4 times 6. The square root of 4 is 2. So that'll give us a 2/3 on the square root of 6. But I warned you. Yeah, when it comes time to normalize, we're apt to run across these irrational numbers. That's when we save the normalization stuff until the end, so we'd have to drag through a bunch of computations with square roots. So, an orthogonal basis is given by, all right, we use Q's. Well, Fraleigh and Beauregard use Q's for the orthonormal bases. Orthonormal. I need to emphasize that. Fix my error. And emphasize orthonormal. Over there we had orthogonal. Now we're making them unit vectors. Orthonormal basis is given by 1 over the magnitude of the first vector times the first vector. That magnitude was square root of 2. So we get 1 over the square root of 2 times vector v sub 1. Here it is, 1, 0, 1. The second vector in an orthonormal basis is v sub 2 normalized. That is 1 over the magnitude of v sub 2 times vector v sub 2. V sub 2 had magnitude, had norm, square root of 3. V sub 2 was negative 1, 1, 1. And Q sub 3 would be 1 over the magnitude of v sub 3 times v sub 3. Okay, the magnitude of v sub 3, was this thing here. Depending on your taste of simplifying this number, if I take a reciprocal of it, we get, how about 3 over 2 on the square root of 6. That's the reciprocal of this. If you want to rationalize any of these denominators, you have a good time. The solutions manual, I'm not sure if they rationalize denominators or not. I mean, we've got a lot of stuff going on to worry about simply rationalizing denominators. I'm happy with that version of that coefficient. And then v sub 3 was this guy. So v sub 3 carries with it a 1/3. And this 2 for negative 2 stuff. Okay, at least I get a little cancellation there. But we found an orthonormal basis. Let's just write up a synopsis of what it is. And whether you wish to distribute those scalars inside of those vectors or not, whatever, you found an orthonormal basis. Okay. So, orthonormal basis would be the vectors q1, q2, q3. q1 is given here. That's 1 over the square root of 2, 1, 0, 1. q2 is given here. 1 over the square root of 3, negative 1, 1, 1. And then this other stuff here. Let's cancel the 3s, so we get 1 over 2 on the square root of 6. 1 over 2 on the square root of 6, 2, 4, negative 2. And there's an orthonormal basis as applied to this original basis. What's wrong with this original basis? Well, it ain't even orthogonal, is it? What's the dot product of these first two vectors? 0 plus 0 plus 2. Dot product's 2. They ain't orthogonal. If they were, some of our computations would have been simplified along the way. So we're taking this basis of kind of ugly vectors, turning it first into an orthogonal basis. Actually, along the way, we were picking up orthogonal bases. That's how we were able to do those projections with all those dot products. Without that, it's more complicated. See section 6.1, where we projected onto subspaces W. You had to find a basis for W perp. That was awkward and part of the motivation for us to go through and look at orthogonal bases at least. So anyhow, we found an orthogonal basis, V1, V2, V3, and normalized it. And there's the orthonormal basis. I bet you those first two, I bet you are orthogonal. So I think we already checked those. Let's check the first and the last one. Are these two orthogonal? What's the dot product? Let's see, 1 over the square root of 2 times 1 over 2 on the square root of 6 times 1 times 2 is 2. 0 times 4, 1 times negative 2. It'd be 2 minus 2. It'd be 0 times whatever happens with those coefficients. Yeah, the dot product's 0. So we're good on orthogonality. And we're good on normality if these computations are correct. And that's the Graham-Schmidt process applied to at least 3 vectors in R3.